Welcome to the third AGILE webinar. And I'm Jing Yao, Co-Secretary of the AGILE Council, and I'll be chairing today's session. I'm joined by my colleague, Dr. Yao Wang, who will be helping out with the Q&A session later. Just a quick practical note before we start. The session is being recorded, and we will have about 10 to 15 minutes for questions at the end. Today's webinar is hosted by the Urban Big Data Center at University of Glasgow. Our speakers are Dr. Rafael Verdugo Torres and Dr. Pengyuan Liu. Rafa is a lecturer in urban analytics and interested in using emerging forms of data and innovative methods to address urban mobility and transport challenges. He will first give us a brief introduction of the Urban Big Data Center and then present his recent work on how the rise of home and hybrid work has affected the implicit value of public transport accessibility. Pengyuan is a lecturer in digital planning. He is a quantitative geographer specialized in geospatial AI and urban digital twin research. Today, he will present his recent work on graph modeling and spatially explicit GeoAI in urban analytics. So with that, I'll hand over to Rafa.
Thank you very much, Jing. I'll try to share my slides. Just a second. It should be there. Can you see my slides? Perfect. Hello, everyone. Thank you very much for joining today. As Jim kindly introduced me, my name is Rafael Verduzco, and I am a lecturer in urban analytics based at the University of Glasgow. So first, I will start with a very quick introduction of the Urban Big Data Center. So I'll give you an overview of what this is and the sort of things that we do here at the Urban Big Data Center of the University of Glasgow. So just to start with, the Urban Big Data Center is both data service and research center. And before I go on, I'd like to mention that the Urban Big Data Center has gone through various phases. So part of the work that I will be presenting corresponds to phase 2. And those two first stages happened between 2014 and 2025. So the topical domains that we cover here at the Urban Big Data Center, I don't know why this slide is not advancing. Some technical issues. I think I'll reshare again, so I'll stop sharing and reshare. So hopefully that should work. Apologies for the inconvenience. Here we go again. Right, okay. So the Urban Big Data Center is both a data service and a research center. And the topical domains which are covered are housing and property, the labor market and the environment, and transport and mobility. So the distinctive character of the UBDC is that we use emerging or non-traditional forms of data and some innovative methods to understand and improve cities. So the type of data that we use to understand these topical domains include platforms that generate data based on the interactions of users and a general transport. So some examples are, for example, Supla, which offers property listing data, Atsuna, which offers job adverts, Strava, which is an active or physical activity application, or Hawk, which collects location data from mobile phone applications. So moving a little bit into the new phase of the Urban Big Data Center. So for prior phases, the Urban Big Data Center has been mostly funded by the Economic and Social Research Council. So, but currently in phase number 3, the center still focuses on both being a data service and a research service, but it is also expanding and putting additional emphasis in some of the innovative methods, which include AI and the use of smart data. So just to give you a flavor of the type of projects that we've been developing at the Urban Big Data Center, so those include traffic and object recognition from CCTV cameras. It also includes housing sensors combined with longitudinal surveys, fluid resilience based on citizen science data, and mapping and urban deprived areas. Moving ahead, I would like to zoom in a little bit in detail with to a project that I have been working in the past few years. So this is around geographic accessibility, and this underpins a family of data products and tools around these concepts. So just to start a little bit clarifying what I mean with geographic accessibility, and I'm sure that a lot of the audience are geographers, so they might be familiar with this concept already, but accessibility indicators measure the ease of reaching value destinations. So what we have done at the Urban Big Data Center is to combine data which is reflecting public transport services, mobility, land use opportunity, and this is resulting in a set of data sets which are reflecting accessibility, or in other words, the effective connectivity across all over the UK. So for public transport services, we have used timetables for both rail and bus services. So based on these, we have computed all-to-all travel time matrices across all of Great Britain. So we have done that at the small aerial unit. So that's approximately at the neighborhood level. So those travel time matrices are reflecting the travel or the a realistic travel time from each data zone to all other data zones which are reachable within certain travel time, given a set of public transport services. So we have also collected data about employment, education, and health. And by combining these, we have estimated accessibility indicators at the national level. So UBDC is offering these different data sets as open access. So it includes timetable archive. It also includes the travel time matrices as open access, and the set of accessibility measures to different types of services. Right. I think I'll go a little bit quickly. I just wanted to give you an example of the type of accessibility measures that we have developed. So some of them include, for example, accessibility to employment, as it is illustrated here in this map. Some others include accessibility to green spaces and so on. So we have also developed an R package, which it is helpful to query these accessibility measures, to tailor new accessibility measures, and to estimate new accessibility measures. So for more information about the Urban Big Data Center, we invite you to consult the webpage and follow us on LinkedIn. So this is a very quick introduction about UBDC, and it also serves as an introduction for the paper that I'm going to be presenting for my own talk. So I think this is it for now about the UBDC. So I'll stop sharing my screen and switch to the other to my other presentation. Right, now moving into the specific presentation that I'm going to be talking about today. So fundamentally, I'm going to be talking about a paper which was recently published. And in this paper, we were interested how the willingness to pay for public transport accessibility as reflected in property prices could have changed after the pandemic. So the details of the open access paper are here. So this paper was published in Environment and Planning B, Urban Analytics and City Science. And this is a team effort, and it is authored by colleagues including Michalis, Nick Bailey, Anna Maria Nisi, and by myself. The background of this paper is, or the main motivation of this paper is because during the COVID-19 pandemic, so there was a rapid increase of the people that were working from home or were doing some hybrid work. So just to give you a quick figure, in 2019, it was about 12% of the workforce that was working from home at least one day a week. But this increased up to 25 and 40% in 2022 in the UK. So something similarly happened in the EU, but it was not as high as the trends in the UK. So some of the impacts that we could expect from this is lower demand of office property. Households can also live further away from workplaces, and an increased housing demand in rural and peripheral areas in the city. But also we expect to see some heterogeneity in the people who can benefit from these alternative shifts. So in other words, there are certain occupations that would be more flexible for working from home compared than others. So that's something that we are taking into account in the research that we have developed. So based on those observations, in the empirical trends in the UK, then we used urban economic theory to try to hypothesize the potential changes in the property market and how that could be affecting the value of public transport accessibility. So we depart from standard urban economic theory, and for most part of it, the monocentric model establishes that housing prices will diminish as distance from the CBD or the central business district, and that is because there is a trade-off with commuting costs. So the higher the commuting cost, the lower the housing prices. And at the same time, we can expect that the size of the dwellings will be larger as we move away from the CBD. But there are some interesting extensions from the monocentric model. So most commonly, we have the polycentric model, where we have different features in the landscape. So one important feature of them is the public transport infrastructure, which can at times fundamentally change the urban structure. So accessibility measures that I was talking about before are capable of capturing some of those polycentric structures of the urban form, and that's why we are using accessibility measures for this work. So the train of thought for this paper is that it all starts with the rise of home working arrangements. So based on that, we can expect that households widen their housing search area. So because they don't need to go to office every day, or they do it less often. So we can also expect that there is a lower cost or more desirability of suburban areas, which are now within reach because people don't need to travel to dense urban areas as often as they did pre-pandemic. So we can also think that people are spending about the same time and money in commuting, but they are doing it less often. Because they are also interested in wider search of area, we can also expect that people will be facing longer journeys. So because of these, the implication is that there will be lower willingness to pay for public transport. So as I said, people will be traveling less often, so they are not as interested as if they were traveling to office premises every day. But as I said before, we expect to see an uneven home working opportunities. So there are certain occupations that can benefit from those new arrangements more than others. So in the end, we expect to see all these changes reflected in how the willingness to pay for public transport can change across different types of cities, which can present different characteristics, but also how that changes across neighborhoods. So based on these, we developed 3 general research questions. So the first one is asking whether there is a change in the willingness to pay for public transport before and after the pandemic. So under the assumption that there is an increased working from home arrangement. So the second question is mostly interested whether there are some difference between cities with different characteristics. So for example, whether there is a difference in the change of willingness to pay according to the size of the cities, for example, smaller cities compared to larger cities, or cities with lower housing affordability, and so on. And finally, the third research question is asking whether there is a difference in the willingness to pay after the pandemic within cities. So that is neighborhoods with characteristics such as increased potential to work from home, or neighborhoods that were relying on public transport pre-pandemic that would be affected differently after the pandemic. So what we did is that we took data from a property listing platform, which is a data set which is collected and offered by GBDC. And this is offered and assembled by a web platform which is called Zoopla, and it is one of the major property platforms in the UK. So the UBDC dataset contains about 11 million property listings for sale, and that covers since October 2016. So regarding the analytical design of our analysis, we cover 74 cities in England, so that's pretty much all of the urban areas in England. And we define 2 periods. So we define the pre-pandemic period, which includes about 1.3 million properties, and a post-pandemic period, which includes a similar size of observations in our study. So on the other side, regarding the public transport data, I already talked about the accessibility indicator that we developed at the Urban Big Data Center. So we use the accessibility to employment to measure the effective connectivity of those public transport services, or more generally, the public transport network to connecting to employment. And because these data set, the accessibility measures are discretized by, for example, the number of employment which is reachable within 15, 30, and 45 minutes. We summarize that information using principal component analysis. So we developed 2 principal components. So principal component 1 is reflecting general accessibility. So let me see if I can have my pointer here. So that's principal component 1, and as we can see, the different time codes are generally equally weighted. So that's why we're calling principal component 1 as general accessibility. And by contrast, the principal component 2, that's strongly reflecting very local accessibility. So that's accessibility within 15 or 30 minutes. So these 2 principal components account for 90% of the cumulative variance. Right. Not moving again. Okay. Oh, okay, there you go. So we use the hedonic pricing model to understand and deconstruct how the different property value is constituted. So what we did for here is, as I said, we defined two periods, pre and post-pandemic, and we used a multi-level model. And that is because we have properties which are aggregated within neighborhoods. We also use the many models approach. So that means that for each city, we fit one multi-level model, and then we summarize those coefficients reflecting the difference in the willingness to pay for public transport in a meta-analysis. So that's the base model that we use, and it is basically interacting the principal component, which reflects accessibility, and the pandemic period, which is post-pandemic. And then in an expansion on a model, we have a three-way interaction where we are interacting the principal component, number one, and some of the characteristics of the neighborhood, for example, their potential for working from home and the post-pandemic period. So moving into the results, so the answer or addressing the research question one, whether there was a difference in pre and post-pandemic, the first finding suggests that pre-pandemic, overall, there was a positive value for public transport accessibility. So on average, and that's across all of the cities, house buyers were willing to pay about 70% for each additional unit in accessibility. But there is some variation within these estimates. So, for example, some cities have shown that there is a negative willingness to pay even pre-pandemic. So what we're showing in this graph is on the vertical axis, on the horizontal axis, we are showing the coefficient for the willingness to pay for public transport accessibility pre-pandemic. So we can see that most of them are on the positive side. So there is a positive willingness to pay for accessibility. And what we have on the vertical axis is the interaction for the willingness to pay for public transport post-pandemic. So what we see is generally a negative trend. And what that means is that post-pandemic, there was a drop. We identify a drop of 3% on average in the willingness to pay for public transport accessibility. So even though that reduction happened across almost all of the cities that we studied, we see that there was a greater negative shift in the smaller cities. So that's a little bit against the prior hypothesis that we had before, because larger cities had more use of public transport. And we can actually see that the blue line is representing big cities, whereas the yellow line is representing smaller cities. So we can see that general parallel trend declining in the willingness to pay for public transport, but it is larger for smaller cities. Okay, so moving into the next research question, which is the difference between cities. We found out that there was a larger drop in cities with low affordability. So that drop in cities with it is expensive to buy a house, there was an average decrease in about 2.5%. However, we didn't find a difference between cities with high or low public transport use before pandemic or cities that has a high potential working from home. So moving to the last research question, where we were asking the difference between neighborhoods, we found that there was on average a 4% drop in neighborhoods with high potential for working from home, but that's confined only to small cities. And there was an additional 3% in the drop of value of neighborhoods, which were in low affordable cities. Finally, we also find that there was on average a 2% drop in neighborhoods with high potential for working from home in combination with high usage of public transport prior the pandemic. And again, this is confined only to smaller cities. So moving into the discussions and take-home messages, I would like to mention that the findings that we have reported in this paper are suggesting a shift in the housing demand towards less well-served areas by public transport. So that means a move to lower density or suburban locations with potentially some implications for lower commutes. So even though people are able to work from home more often, that doesn't necessarily mean that the total commute in terms of money or potential emissions is lower than it was before. So we also observed that there is a fall in the value of land, which is around public transport areas. And we could also expect that there would be a lower demand of public transport services, particularly in smaller cities. So overall, I think the results are pointing and are calling for greater urgency to recognize the value of public transport as a public service itself. And we would expect that public transport services would be harder to finance public transport services in the smaller cities. And those are greater risks and should receive larger attention from government. So this is it from me. Thank you very much for listening, and hopefully I didn't exceed the time too much. So I'll stop sharing my screen and pass it over to Penguin.
Thank you so much. I will share my screen as well. All right, I hope we can see that. Yeah, all good? Cool. So hello everyone. So my name is Penguin Liu, and I'm going to talk about my research about living upon networks, graph modeling, and spatially explicit GeoAI in urban analytics. It's not only about one research, it's actually about all kinds of research that I did in my past years, to be honest. A brief introduction of myself. I coming from a computer science background, and then I got a PhD in geography, and then I work across different kind of institutions across Europe and Asia. That's basically because of this kind of like background of mine. I'm pretty much looking at urban issues naturally from a methodologist perspective. So I'm looking for analytic or computational kind of driven analytics methods into the urban problems. So a brief introduction to start my talk today is that cities used to be designed based on tuitions. What does it mean is because like in early stage of urban planning, usually those kind of planning or the real urban implementations based on the designer's intuition, such as our famous kind of concept of garden cities and zoning laws that everyone is pretty much aware of. However, because of the technologies, I would say that we are witnessing our urban planning are increasingly based on the evidence. For example, from a geography perspective, we increasingly have emphasized this kind of 15-minute cities concept in any kind of designing practices, and also we are using fancy technologies such as digital twins in order to modeling the urban environment. Recently in Shanghai, I realized that there is even this kind of quantum city concept raised up by the Chinese scholars, which I'm not entirely sure how that's going to turn out, but that's basically how our urban planning in the real life are depending on the new technologies these days. So as every single report or the paper starts their beginning sentence instance, right, over 60% of world population will be living in the urban areas. We can see that we're living in a complex urban systems. And urban science, because of that, is undoubtedly a science. So every day we are generating millions of data for all kinds of purposes. So we are living so-called big data era. In terms of big data, we saw many kinds of data in our everyday life, such as all kinds of census data collected from the smart buildings or Internet of Things. We also been increasingly use this kind of crowdsourcing data, such as social media, in order to analyze specific urban issues happens worldwide. Meanwhile, instead of like text data, we are heavily using the imagery data, such as the satellite image from the sky. Meanwhile, we are also witnessed increasing use of street view images that basically can take the eye-level pictures of our urban environment to contributing to our urban analytics. So wait a minute. So it seems that all the data I introduced in the past, probably 30 seconds are georeferenced, which is actually true. Over 80% of data generated every day are actually georeferenced. So as urban planners, we're pretty much drawing our little city on this kind of urban modeling system based on those kind of georeferenced data we collected every day. So because of this data, right, we're actually generating so much data every day. How could we actually make use of this data? Here actually comes with the artificial intelligence. So in terms of artificial intelligence, well, I put this famous pictures from the movie, right? But I'm not saying like artificial intelligence is there yet, but maybe one day, who knows? So artificial intelligence is not really a new concept. Actually, date back in the 19th centuries, we already seen this concept saying that maybe one day the computer can actually do as humans. And actually, since 1950s, we are increasingly to see the evolution of artificial intelligence in our everyday life, from Turing test invented in 1950s and to nowadays, pretty much every one of us are using large language models for our everyday tasks. Because of that, we actually see a lot of research applying AI techniques to the spatial problems, such as one of the paper I did when I was a postdoc in Helsinki is that we're actually looking at social media data, trying to extract where those kind of areas having the sports facilities, and we compare with the official data, trying to identify those kind of sports facilities that were hidden and not really recorded by the public, by the officials. In the meantime, we're also seeing that people using street view images to doing many things. For example, one of my colleagues in Singapore actually used the street view images in order to identify the urban soundscape, which is quite fascinating because they are detecting the soundscape or the noise level directly from the images. But all this kind of research seems that AI here used being as a tool. If AI just being a tool used by us, then why we are not replaced by computer scientists right now? I think our discipline is probably more than that. So instead of only applying AI to the spatial problems, we need to bring a spatial concept back to the AI. So, well, how do we actually do that? We need to talk about these fundamental questions in AI first. That is the prior. Prior is basically the concept, the teaching the machine what they are looking at. For example, in this image here, we're teaching the machine what is an apple, so that machine eventually, after the learning process, it will learn what is an apple. So if prior is that easy, what kind of priors we have in geography then? In geography, we actually have so many kind of geographic priors, such as the very famous Tauber's first law of geographies, such as our fundamental spatial concept of spatial heterogeneity or location theories, all kinds of things. But how do we actually bring those kind of geographic prior back to the AI systems? Here comes the graph. That's basically what I'm talking today. So from geography perspective, graph has long been used in geography and geoscience. It's been used to represent networks such as transport networks, street networks, space syntax, or social networks, all kinds of things. So we have been long used graphs to actually to represent our complex world, right? And up until the recent years, there's this new type of technologies being invented called graph neural networks. So two of the famous techniques are actually called graph convolutional neural network and graph search. I'm not going to have math lessons here, but I'm just putting here to let you know there is this kind of technologies being invented, and we are using them to deal with the urban problems. And the fundamental the fundamental mechanism of the graph neural network is basically about message passing. Well, it's actually more about node information aggregation and the message passing. It's basically taking one node and trying to aggregate all the information from its neighbors and building on the neural network architecture, trying to pass these kind of nonlinear interactions among all the urban entities we are modeling for the prediction or for all kinds of tasks, such as node classification, link prediction, graph classification, all kinds of tasks we are actually dealing with. So how do I actually use this kind of graph neural network in my own research or in the urban analytics driven? Some of my research, I will start with bringing this kind of first law of geography in the urban analytics from the social network first. This research was conducted when I was a PhD student at University of Glasgow with my PhD supervisor, Steph Dispata, and we've been conceptualized this social media post as a spatial temporal element on the urban surface. So we're taking all the Twitter data, now it's called X, Twitter data, and we're looking at where they are located and when they were posted. And then we constructed all kinds of like spatial temporal graphs in order to modeling these social networks. So the underlying assumption here is that if the two posts are close to each other, they're likely to have similar activities. And this is one of the earliest work embracing this idea of spatially explicit GeoAI, and we demonstrate that by using this kind of spatial explicit graph, we'll be able to more precisely classify the urban activities reflected on social media. And the second research I would like to take in the first law of geography is actually on street networks. Street networks, as I just mentioned, has long been used as a network understanding of the urban environment. In this particular study, it's called Extendable Spatial Explicit GeoAI for Urban Analytics. In this study, we conceptualized the street networks into a graph structure. And we're taking this graph neural network, we take the street networks using the graph neural network to do two things. The first thing is about the traffic volume. The second thing is about to predict the administrative population volume. And all the graph neural network will be able to produce relatively good prediction accuracies in terms of the traffic volume and the population volume. But based on that, we applied a separate technology called GNN Explainer, trying to explain what factors actually leading to the high traffic volume. Could be the narrow of the road, could be the openness of the road, or could it be just there are traffic lights, so there could be more traffic, or there are just more pedestrians, so the traffic here might be busier or less busier. So this provide a tool for the urban planners, or provide kind of like intuition understanding or the preliminary understanding of the urban area, saying that if they actually want to say increase the urban population or decrease the population, what kind of interventions they might actually implement might actually work. And then moving from the street networks, we also apply this kind of network understanding or the graph understanding of urban areas on small areas in the UK. This is one of the studies we conducted. Well, I conducted with my PhD supervisor on the census geography. We're applying the graph understanding of the urban areas based on so-called sensor tracks in London, and by applying this kind of graph understanding, sorry, it's probably too quick. So by applying the graph neural network on this kind of network understanding of sensor tracks, we'll be able to generate a kind of embeddings that could be geographically aware embeddings. So what does that mean? Actually, there's a background story to introduce here. The geodemographic classification has been long relied on the K-means clustering, but K-means, as a traditional statistical understanding of the census geography, they treat each independent sensor data as statistics rather than considering where it located. So our method, by applying this network understanding of the census data, we'll be able to generate this kind of embeddings that taking both the census data and also where they are located into consideration. This is a new method for creating a spatially aware geodemographic classification, and it's basically thinking census data beyond statistics itself, but a geographic objects with the locational information. And we prove that by using our method, the geodemographic classification as an output will be similar, will produce more spatially aware geodemographic classifications in the urban areas. And meanwhile, we see that these kind of neural networks also works on urban objects such as buildings. So we're taking the graph neural network models on the buildings across different kind of urban areas. In this particular work, we apply the graph neural network to do two tasks. One is regression, one is classification. In the regression task, we are predicting the building height, also the building stories. And for classification task, we are trying to fill in the 3D semantic information such as the building type, building age, building materials. And by applying the neural network across three different urban areas such as Boston, Melbourne, and Helsinki, we realized that even with 10% of training data available, our model will already be able to produce reasonable prediction accuracies. That gives us the confidence that in the future, if we want to actually fill the gap between of the 3D urban morphology data, we can use our models. Similarly, another similar task, we apply the graph neural network on the network's modeling of the buildings on the buildings. We apply this kind of method to the local climate zones. So traditionally, local climate zones are very closer, meaning that they're looking on the grid-based data, but our method will target it on the buildings directly. And by applying the graph neural network, we'll be able to downscale the local climate zones to the building level. And we're also applying the graph neural network on the spatial interactions by taking the pedestrians walking on the path and their spatial interactions with the surrounding 3D urban morphologies into consideration. In this particular work, we let the participant to work on the pedestrian path in the National University of Singapore. And by applying a neural network called GraphSearch stacked with the LSTM, we'll be able to predict the urban outdoor comfort by the humans. And in this particular work, one of the novelty is that how we actually construct this temporally varied graphs in the urban study. So at one point, a pedestrian might encounter both cars passing by or the people passing by, but at the next time step, maybe the cars will be gone, or at the following time step, maybe both the cars and pedestrians are gone. So actually, in our everyday working activities, our surrounding urban situations always changing. So in this particular work, we'll be able to capture this kind of dynamic, varied spatial interactions with surrounding environment and using the graph neural network to model them. That's basically how the structure would actually look like. So we can also stack different kind of graphs together. One of the recent publication last year is that we are trying to model multiple geographic laws together. In this particular work, we're trying to combine the first law of geography, looking at proximity-based graphs, together with so-called third law of geography, meaning that if two areas are having same kind of classification, they probably share some underlying similar geographies. So we use this so-called new technologies called, well, not really new, but this kind of new idea of hypergraph in order to model all kinds of spatial interactions together to predict the climate justice map. And we also combine different kind of graphs together. For example, the street networks together with the waterway connections together in Singapore to generate this kind of spatially aware embeddings. Based on embeddings, we'll be able to predict the land surface temperature as well as the social housing price in Singapore. And we realized that by using this kind of sophisticated or holistic urban modeling together with urban waterway and also the street networks, we'd be able to predict the land surface temperature without additional information. So traditionally, this kind of tasks require quite a lot of like data, but we realized that by using this kind of holistic understanding of the urban networks, it can already produce good results without extra information. We also say some neural networks. We are also exploring more use of neural networks. In this particular work, which published in last December, is that we be able to construct this kind of hierarchical spatial graph, basically help us to do this kind of downscaling work for small area estimation, so that sometimes in most of the socioeconomic data we are facing the fact that we probably only have data at a very large scale, and by using the graph neural network or this kind of hierarchical spatial neural network, we'll be able to predict small data based on the large scale data. So in that sense, it's a small area estimation. So at this stage, you might think, oh, this technology is very complicated or very fancy. Can I actually learn that? I can say that you can, because last year I did this kind of workshop in Tongji University's workshop. Basically, it's an 8-day workshop, and most people who attended the workshop has no prior experience with graph neural network. But by the end of this workshop, every group produced this kind of very fantastic urban analytics task of their interest, from urban crime to urban climate modeling. So I would say if you are interested in this topic, you are more than welcome to explore, and it's not that complicated, I would say, and you are more than welcome to approach to me. So here are So by the end of it, here are some of my 2 cents. I think city models need to address and leverage a large number of different dimensions of knowledge based on spatial graph. And at a high level abstraction of these structures can be described with graph and nodes. And spatial structures and geographic pros are actually the key to be involved to develop those spatially explicit models. And I believe graph is fun, and there is so much to explore. So if you're interested in this topic, you're more than welcome to contact me. Thank you so much for your time.
Thank you so much. Thanks again, Rafa and Pengyuan. Yeah, fantastic talks and lots of information here. Okay, now I believe our audience have some questions here. We have about 10 minutes for questions and comments. Yeah, you can put your questions in the chat, or you can raise your hand. I can unmute you. No questions, no comments?
I probably talk too quick because I was a bit concerned at the time. Yeah.
So okay, I can start with a quick question for Pengyuan. Yeah, you showed us a lot of examples, how the graph models can be useful to address urban challenges, in all kinds of different domains. So my question is, are there any spatial problems that graph models are not good at, or not that so good at?
Yes, there are. So there is the one specific issues with the graph neural network is about the oversmoothing. So when using the graph models, it can rarely scale up, meaning that the neural network architecture usually stuck as 2 layers or 3 layers, because once the layers scaling up, the over smoothness issues will come in, so that all the node embeddings will tend to be similar to each other, and that's the issue when you want to do large scale analysis, meaning that it can probably perform well in the urban scale, but when you actually want to do, say, a nation scale tasks, it's always been very challenging. But a good thing about that is that my PhD supervisor staff, well, he got a fellowship, is actually dealing with this kind of graph-based foundation models, and probably can somewhat solve it in the future, and we are working together towards this direction. So I don't know, that's basically a challenge, but also fun for me to explore in the future.
Okay, there is a question here. I can unmute our audience. How to do that? Allow mic. Yes, Sato, you can.
Oh, can you hear me?
Yeah. I just unmuted
Okay.
you. Yeah.
I mean, I wrote it down. Thanks for both of the talks. And I'm really interested in GNN personally. I'm working on that kind of things. I just have the question, like, to what kind of aspect is GNN somehow spatially explicit compared to the other models, like, for example, I don't know, CNN or any other deep learning or even non-deep learning models, like how is it kind of spatially explicit? I just wanted to hear some opinions.
Yes. So this is actually a good question. I actually deleted one slide before the talk. Now I regret that. So in terms of the GNNs compared to other spatial models, first of all, we use GNN to explicitly incorporate the spatial interactions in the model. So normally, if you're looking at the CNNs works well with the grid data, right? But our world is not really the Lego land. What I mean is that our world is not consist of the very grid data lined altogether. Actually, you know, as in geography, we know that all kinds of spatial data could presented in all kinds of forms when they are together. They could be stacked together, they could be separated, they could be overlapped. All these kind of things, CNNs cannot really be effectively deal that, but GNNs, because it can explicitly incorporate the spatial interaction, you can define those kind of interactions by yourself, meaning that you can define whether the link between the two nodes will present overlapping, will present separate, will present neighboring architecture. It has the capability to explicitly incorporate those kind of spatial interactions between the geographic objects. But in the meantime, GNNs is not explicitly dealing with the coordinates itself. It's more of dealing with the spatial interactions, if that makes sense.
Oh, great. Okay. I'm on the same page, to be honest, actually. Thanks, Sarah. Yeah.
Thank you. Thank you for your question.
Thank you. Other questions or comments? Yeah. So yeah, I can ask another question. So for Rafa, yeah. So at the end, the end of your talk, I saw you have some take-home message, right? So regarding the implications of your findings, I'm just wondering because your work is closely related to the public policy, both in terms of like transport and housing. So have you like communicated with the local authorities or stakeholders about your findings and whether like it is possible, like you know, they will incorporate your findings in their future, like policy making?
Yeah, thank you, Jing. That's an interesting question. And yes, I think the results of this study are quite relevant to policy and particularly to policy in England. So at the same time, I think there are like different angles that that you can take from the results. So the first one, as we saw, is from the side of urban planning. So we are seeing a kind of despairing sort of landscape in terms of that there is more interest in, like moving into suburban areas, and at the same time, less interest in locating in areas that are well served by public transport. And I think it is particularly worrying that we have shown that that those decreases in the willingness or in the interest in public transport are affecting small cities the most. And I think that has a particular large implication for smaller cities because they tend to have less robust public transport systems. So in other words, I think it really depends on the governance scheme for operating public transport systems in England. So that basically operates under a market-based approach in most of the cases, pretty much except London and Manchester. So that means that we can expect the public transport systems to be having a hard time post-pandemic. So that should call for greater attention from government to support those kind of systems. We haven't been in touch with local authorities or with the Department for Transport, but yeah, we believe that it would be quite relevant for them.
Okay, thank you. So one quick last question from Yang.
To unmute myself. So very quick question for Rafa. So I'm not seeing details of the modelings, but quick question about whether you control any factors after the pandemic, such as rent cap, and also in housing domain, there are a lot of controls going on to protect tenants, for example, and then these will have no knock-on effect on housing prices. And also there are some energy crisis after the pandemic as well. So have you taken into account those factors in your model? Thank you.
Yeah, that's an interesting question as well. The short response is no. We haven't taken into consideration those small details, but I think the kind of big assumption is that we can expect that those things will be mostly affecting the market like heterogeneously. So far, I don't know. I can see how it can affect some cities more than others, but that's an interesting hypothesis for further kind of studies. So yeah, again, short question is no, but yeah, do you have some sort of hypothesis how these kind of policies or events could affect in a heterogeneous way the property market?
Okay, thanks. That brings us to the end of today's webinar. Thank you again, Rafa and Pengyue, and also thanks to everyone who joined us today. Yeah, so the recording of this session will be made available on the AGILE YouTube channel. And our next webinar will take place in May, led by University College London. So please keep an eye on the mailing list for the details. We hope to see you again at the next AGILE webinar, and have a great rest of your day. Bye.
Thank you. Bye-bye.